In this video, we're going to take a look at empirical and molecular formulas from percent composition. We're going to do it looking at a compound that's familiar to most of us, caffeine. So we're told that a typical cup of coffee or tea has a caffeine content of about 0.1 grams. We're told the molar mass of caffeine is 194.22 grams per mole, and the percent composition by mass for caffeine is 49.47% carbon, 5.20% hydrogen, 16.48% oxygen, and the remainder is nitrogen. So the first two questions are a little bit of review of basic stoichiometry, and then we're going to jump into the empirical and molecular formula. So first of all, how many molecules of caffeine would be present in a typical cup of coffee or tea? If you know what you're doing, pause the video and try to do the calculation yourself. So to figure this out, I'm going to use this information that there's 0.1 grams in a typical cup of coffee or tea. So I'll take 0.1 grams of the caffeine, and I'm going to convert the grams of caffeine to moles of caffeine. And whenever I see grams and moles together, I realize I'm looking at a molar mass. And that was given to us in the question above. 1 mole of caffeine has a mass of 194.22 grams. The molar mass is the mass, grams, of 1 mole of the substance. And now we're going to convert the moles of caffeine to molecules of caffeine. The question was how many molecules are present. When you're converting from moles to particles, whether it's molecules or atoms, Avogadro's number comes into play. 1 mole of anything, according to Avogadro's number, contains 6.022 times 10 to the power of 23 things. So in this case, there's that many molecules of caffeine in 1 mole. So now we can grab a calculator and evaluate this. Be sure you're using the scientific notation button when you're doing your Avogadro's number. So 0.1 divide by 194.22, and then multiply by Avogadro 6.022, the scientific notation button, and then 23, the exponent, and I get an answer of 3.1 times 10 to the 20. Now in this worksheet, there's only one sig fig on the 0.1, so really I should say 3 times 10 to the 20 molecules of caffeine. Only one significant digit in that answer. For part B, we are told that in an experiment we need 0.050 moles of caffeine. So how many grams should we use? What mass should we use? That's a very common practical problem that you would have to encounter in a lab. An experiment calls for a certain amount in moles, but we need to measure it using an electronic balance, so we want to know how many grams should we use. So this is a 1 unit multiplier calculation. See if you can pause the video and try that yourself. So 1 unit multiplier because we're just converting moles to grams, and that is the molar mass. 1 mole of caffeine, 194.22 grams. So doing some either mental math, right? You can think of 0.1 times 194.22 would be 19.4. 0.05 is half of that, so half of 19.4 would be the answer, about 9.7. Or just grab the calculator, 0.050 times 194.22, and keeping 2 significant digits, we had 2 digits in the original moles, we get 9.7 grams of caffeine. So those are just 2 quick review problems. And now we're going to jump into the newer topic, so how to find an empirical and molecular formula for caffeine, noticing that we were given the percent composition of the compound as well as the molar mass of the compound. Now, what is an empirical formula? Let's think about that just for a minute. An empirical formula. Let me take a simple example of glucose. It's a very commonly used one. So C6H12O6, that's the molecular formula, or the chemical formula, for glucose. An actual glucose molecule has 6 carbons, 12 hydrogens, and 6 oxygens. However, notice that we could reduce this somewhat. Just like you could reduce 6 over 8, you could divide everything there by 2 and you can get 3 over 4. We can reduce this formula because 6, 12, and 6, we can divide everything by 2, for example, and get C3H6O2. We could reduce it even further. We could reduce it all the way down to CH2O. That would be the most reduced form of that compound. Now, if I asked you, in these 3 particular formulas, how does the percentage of carbon compare? In other words, how does the percent carbon in the first compound compare to that in the second, compare to that in the third? Well, if you think about fractions for a minute, equivalent fractions, 6 over 8 is equal to 3 over 4, in both of those fractions, you have 75%, don't you? 3 over 4, 0.75, 6 over 8, 0.75. It's the same fraction. So in all 3 of these formulas, the percent of carbon, the percent of hydrogen, the percent of oxygen would be the same. If you don't believe me, just take a moment, pause the video, and calculate them. For the first one, 6 times 12, the molar mass of carbon, divided by the molar mass of the glucose. That's the percent carbon, times by 100. Do the same thing in the second formula, 3 times 12.01, divided by this molar mass, times by 100, or 12.01 divided by this molar mass, times 100. And you'll get the same percent carbon in each situation. The most reduced form of the formula, the simplest form of the formula, is what we mean when we say the empirical formula. So the simple definition, if you want, of an empirical formula is that it is the simplest formula of a compound, or the most reduced form. Now remember that the empirical formula is not the actual molecular formula of the compound. In glucose, there are 6 carbon atoms for every molecule. So telling me the empirical formula is CH2O is helpful, but it doesn't tell me what the actual molecular formula is. Instead, it simply means in the glucose molecule, there's 2 atoms of hydrogen for every 1 atom of carbon. There's 1 atom of oxygen for every 1 atom of carbon. It tells me the ratio of the atoms, but not the actual numbers. So remember that. So what we're going to do is find the empirical formula of caffeine, and then somehow, which I'll reveal at the end, we're going to go back to find the molecular formula. If I know the empirical formula, we'll be able to go back to one of these, or even higher, and we can choose a molecular formula from above, but we'll see how to do that in just a few minutes. So if you think you know what you're doing, pause the video, take the information from above, and try to go find your empirical formula. If this is your first time doing this, or you're just reviewing, then follow along with me. So the first thing I'm going to do is, because the question told us percentage composition, I'm going to start my answer by saying in 100 grams of caffeine. I'm going to pretend that we have 100 grams of caffeine. The reason I'm doing that is because these numbers are percents. So if we have 49.47% carbon and we have 100 grams of caffeine, then we would have 49.47 grams of carbon. Similarly, if there was 5.2% hydrogen and we have 100 grams of caffeine, there would be 5.20 grams of hydrogen, and following along there'd be 16.48 grams of oxygen. Now it said there was also nitrogen. How am I going to figure that out? Well, The total was 100 grams, or 100% if you want, so these numbers have to add up to 100. So if we just take 100 and subtract these numbers, we'll get the mass of nitrogen. So 100 take away 49.47, take away 5.2, take away 16.48, there's 28.85 grams of nitrogen in that 100 gram sample. Now, what are we going to do with these numbers? Well, think again about a chemical formula. When we say C6H12O6 is the formula for glucose, we could mean one of two things. We could mean that there's 6 atoms of carbon for every molecule of glucose, or what we would do now, I hope, is realize that we can think of that in terms of moles. In 1 mole of glucose, there's 6 moles of carbon. In 1 mole of glucose, there's 12 moles of hydrogen. In 1 mole of glucose, there's 6 moles of oxygen. So we realize that a chemical formula is really a ratio of moles of substances. So what I'm going to do is take these masses, because we're trying to find the chemical formula, we're going to convert them all to moles in order to get ratios of moles, which is what a formula is. So let's get rid of the grams of carbon and switch to moles of carbon. Let's get rid of the grams of hydrogen, switch to moles of hydrogen. Let's get rid of the grams of oxygen, switch to moles of oxygen. And let's get rid of grams nitrogen, switch to moles nitrogen. Now, grams and moles, we've said before, is a molar mass. So this is the molar mass of carbon. So from a periodic table, we see that 1 mole of carbon weighs 12.01 grams. We see the molar mass of hydrogen. Similarly, 1 mole of hydrogen weighs 1.01 grams. Be sure you see where those numbers are coming from. Don't just copy that. They're on the periodic table, the molar masses. 1 mole of oxygen, 16.00 grams. 1 mole of nitrogen, 14.01 grams. So now, 49.47 grams. If the molar mass is 12, it means we've got more than a mole. In fact, we have more than 4 moles there, or just around 4 moles. We divide that by 12.01, we get 4.119 moles of carbon. Now, a note about rounding off answers: it's better to keep an extra significant digit than it is to round off too much at this point. So don't round off these answers too much. 5.2 divided by 1.01, 5.2 divided by 1.01 is 5.15 moles of hydrogen, 3 sig figs there. 16.48 divided by 16, 1.030, 4 sig figs, moles of oxygen, excuse me, and 28.85 divided by 14.01, 2.059 moles of nitrogen. Now, looking at those 4 moles, I'm not quite seeing a chemical formula yet, but notice that the oxygen moles was the smallest number. So that's the smallest number of moles. The reason I note that is because remember that a chemical formula is a ratio of moles. So what I'm going to do now are some mole ratios. Okay, so let's take the other moles, carbon, hydrogen, nitrogen, and divide each one by the smallest one, which in this case was oxygen. So if I take the moles of carbon, divide by the moles of oxygen, what would that ratio be in the compound? Well, it's 4.119 divided by 1.030. You see where those numbers came from. Equals, grab your calculator, and the calculator gives me a very nice number. It says 3.999. That's really nice because it's essentially 4. Now let's put in some units. This is moles of carbon And look what I'm going to do here. For every 1 mole of oxygen, right? We divided by the moles of oxygen. So I'm trying to express it as a ratio. So that means 4 moles carbon for every 1 mole oxygen. Now, when rounding off, be a little bit careful. 3.999, yes, that's 4. 3.99, yes, that's 4. 3.8, no, that's not 4. Okay, so don't be too liberal in rounding off. If you get something like 3.8, we have a small problem, which we'll deal with in a later example. So moles of hydrogen over moles of oxygen, we're always dividing by the smallest one, is 5.15 over 1.030, and that's going to be exactly 5, it looks like. So 5.00 moles hydrogen for every 1 mole oxygen, which means 5 exactly hydrogen for 1 mole oxygen. And finally the nitrogen, moles of nitrogen over moles of oxygen, and that's going to give me 2.059 over 1.030. That's going to work out very nicely again. It works out to be 1.999 moles of nitrogen for every 1 mole of oxygen. And that's going to round off very nicely, 2 moles of nitrogen for 1 mole of oxygen. So now the formula, the empirical formula, is staring at us right here. So our empirical simplest formula of this caffeine, let's write the formula. And when we write the formula for organic molecules, normally we do it in the order carbon, hydrogen, oxygen, and then any other elements. So in this case, nitrogen last. So we see that in the ratios there's 4 moles of carbon, so C4. H5, there's 5 moles of hydrogen. Now each ratio has 1 mole of oxygen, so we just put O. And then there's 2 moles of nitrogen, so N2. There's the empirical formula of caffeine. Okay? Now how do we go from there to the actual molecular formula? It's like, coming back to our glucose example, if you know the empirical formula, how do you go figure out what the actual molecular formula was? How would you know, for example, up here, that the molecular formula is 6 times bigger than the empirical formula? Why isn't it 2 times, or 3 times, or 4 times? Well, the answer is the molar mass. Remember that we were told in the question that the molar mass of caffeine was 194.22 grams per mole. If we take a periodic table and figure out the empirical molar mass, what is this thing's molar mass, then we can compare it to the actual molecular formula's molar mass and get the multiple to multiply by. So let's grab a calculator. We want to say 4 carbons, so 4 times 12.01, plus 5 hydrogens, 5 times 1.01. Now usually at this point you don't even have to include these decimals. You could just say 4 times 12 and 5 times 1, plus 1 oxygen, so 16.00, and then 2 nitrogens, so 2 times 14.01. The empirical formula's molar mass is 97 grams per mole. Now remember, the actual molar mass was 194.22. So if I take the molar mass and divide by the empirical mass, we get 194, I'm just going to round that off, over 97, which is 2. And when you do this little fraction at the end, you must get a whole number, or something very close, like 2.01. If you don't, you've done something wrong. So what does this 2 mean? Well, the molar mass of caffeine is twice as big as the molar mass of my empirical formula. Therefore, the molecular formula of caffeine is twice as big as the empirical formula. I'm going to go backwards here. Therefore, the molecular formula, the actual chemical formula of caffeine, is twice the empirical formula. So instead of C4, we have C8. Instead of H5, we have H10. Instead of O, we have O2. And instead of N2, we have N4. So we multiplied by 2 because of this ratio 194 divided by 97. So there we have it. We took the percent composition. We assumed we had 100 grams of the caffeine. We found the masses of the elements in the caffeine, converted those to moles. We then chose the smallest number of moles to calculate mole ratios with all of the other elements in the compound. From those mole ratios, we rounded off and got the empirical formula. We took the empirical formula in a periodic table to find its molar mass, in this case 97. That's 4 times 12 plus 5 times 1 plus 16 plus 2 times 14. The molar mass was 97. We divided the molar mass of the compound divided by the empirical formula's molar mass to get the multiple by which we multiply that empirical formula to get the molecular formula of the compound. So I hope that helps with empirical formulas and molecular formulas from percent composition information.